Over the last few weeks, there's been plenty of talk about logistic curves, exponential growth, and the concept of flattening the curve. Unless you've been living under a rock, you know that social distancing and good hygiene are important components of flattening the curve. But what does it really mean to flatten the curve mathematically? All of these concepts are closely related to what we've learned in calculus about derivatives and integrals. I'm about to go into how those concepts are related. Remember these formulas from pre-calculus? We use them to model exponential growth. Whenever a quantity grows by a percentage, these equations can be used to represent the amount after a period of time. The key feature of exponential growth is that because it grows by a percentage, the larger the value is, the faster it grows. That's why an exponential model grows faster and faster. We started with the simplest exponential equation, which calculates the final value after t years with the yearly growth rate of r. This is a pretty good formula for estimating values, but it's not all that realistic. Populations don't grow or shrink once per year. Neither do mortgages. And unfortunately, because mortgages change every month, the amount of interest you have to pay increases every month if you don't pay down the balance. Banks and lenders generally compound interest monthly or daily. We use the second formula to more accurately represent this growth for problems involving money. But again, although this formula is closer, it's still not entirely accurate for true exponential growth. Populations aren't changing once a day or even once an hour. The change is continuous. This is why mathematicians introduced the number e. E is defined as the limit as n goes to infinity of the quantity 1 plus 1 over n, all to the nth power. You can see the similarity between e and the compounding interest formula, which led us to the PERT formula. This is a more accurate way to represent anything that compounds continuously. The PERT equation does accurately represent exponential growth, but we never really talked in pre-calc about where it came from. That's because it comes from a differential equation, which is the equation of a derivative. This equation shown here, dy dt equals r times y, shows that the rate of change in y, or the change in the population, is some portion of the current y value, and the r, of course, represents the percent. To solve this differential equation, we need to do some math that we didn't quite get to in calculus, but it would lead to the solution y equals pe to the rt. This equation works perfectly well for exponential growth. The problem with the equation is it doesn't actually model a pandemic very well. The equation assumes unchecked growth. In other words, it assumes that things can keep growing at the same rate forever. In reality, a pandemic has a limiting factor. At the beginning, the growth is virtually unchecked, but as time goes on, there are fewer and fewer people left to infect. As a result, the growth is modeled not by the equation dy dt equals r times y, which says that the rate of change is a portion of the y value, but by the equation dy dt equals ky parentheses p minus y. This says that the rate of change is proportional not only to the y value, but also by the number of people who haven't been infected, p minus y. As y gets closer and closer to p, this rate begins to get smaller and smaller. Let's take a look at this logistic curve. Notice that the slope of this curve is always positive, and the curve is steepest right in the middle of the graph. This means that if we were to graph the derivative or slope of this function, we would want something that has positive values everywhere, but is at its highest point right in the middle of the graph. So again, the derivative is going to have all positive values, but highest values in the middle of the graph. This is what's called a normal curve, also known as a bell curve. Notice that the values are always positive, but the function reaches its highest point right in the middle of the graph, just as we said the slope of the logistic curve should be doing. In other words, the normal curve is the slope, or the derivative, of a logistic curve. When we talk about flattening the curve, it's usually not the logistic curve that we are showing. We are talking about flattening the normal curve. So flattening the curve really refers to decreasing the values of the derivative, or the slope of a logistic curve. We are literally trying to slow down the logistic curve by decreasing its slope. Okay, so let's move on from the first derivative of the logistic curve. What about the second derivative? Remember that the second derivative of a function refers to the slope of its slope, or how fast the slope is changing. In physics, we'd refer to this as the function's acceleration. There are two ways to examine the second derivative. The first way is to use the original logistic curve. On this graph, the second derivative appears as concavity. When the function is concave up, it's accelerating in the positive direction, so the values of the second derivative are positive. When the function is concave down, its second derivative has negative values. In this case, looking at the logistic curve, we can see that the function is concave up, or smiling, for the first half, and concave down, or frowning, for the second half. So its second derivative would have positive values for the first half and negative values for the second half. The other way to examine the second derivative is to look at the first derivative, which is the normal curve, and consider its own derivative or slope. The slope of the first derivative is positive until the function hits its peak, and then negative after that. This means that the second derivative has positive values until the peak, and then negative values after that. Regardless of which way we figure this out, we can see that the function's second derivative has positive values until a point right in the middle of the curve, and then negative values. This point at which the second derivative changes signs, or the function changes its acceleration, is called the inflection point. On a logistic curve, the inflection point is incredibly important. Because the curve is symmetric horizontally and vertically, this inflection point occurs exactly halfway through the curve. This means that reaching the inflection point is an indication that if we double the elapsed time, we should be reaching the end of the curve. It also means that our total number of infected people should be double the current number. When scientists and politicians discuss the peak of the coronavirus, they are using the work that mathematicians have done to estimate the location of the inflection point. As you can probably imagine, a lot of effort has gone into trying to find the inflection point. According to Dr. Shannon Bennett, a virologist and chief of science with the California Academy of Sciences, that's the burning question for all of us. When will we detect the inflection point in new cases? And once we detect it, how long do we have to run over the crest of the wave before we're on the other side? And of course, real-life data doesn't always follow a mathematical model precisely. When you look at a graph of daily new cases worldwide, or the derivative, it doesn't follow a smooth normal curve. There are several factors for this. First, data is not being reported continuously, and it's being reported at different rates by different countries. Secondly, testing is not happening at equivalent rates throughout the world. As we know, the US has lagged behind other countries in the availability of testing, and many of those with coronavirus symptoms have not been tested at all. Still, it is important to evaluate the data and determine whether or not the inflection point has been reached. Take a look at this worldwide data. What do you think? Have we already peaked? Now let's look at the data from Italy. What's your impression of this graph? And what about the US? Have we reached the crest of this wave? These are truly unprecedented times. As we continue on through this global pandemic, it is important to think mathematically about what's happening. Remember to evaluate the data for yourselves and use it to draw conclusions about what's really going on, regardless of what politicians and TV news anchors seem to think. It has never been more important to think mathematically.